dp on dt equals rp1 minus p. Same rules as before applies. You're going to bring your p's to one side and your t's to the other side. So dp on rp1 minus p equals dt, and as always, you're going to integrate that. The right hand side is easy. The answer is just t. This bit here, I'm going to show it the extension 2-way, just in case it becomes a state ranking style question in extension 1, which means you have to be creative yourself. At least we have it down pat. If not, then like I said, part A, they'll usually tell you to prove what I'm about to tell you, or whatever I'm about to show you. All right. The reason why I say that is because I'll just go scroll out for a second. If you look at these, so this was like 2008 extension 2 HSC, 1992 3-unit HSC, but look at this one, 2016 2-unit HSC, question 16. So even though it's an extension 1 topic that just got released last year, it was asked in 2016 as a 2-unit question. But it's question 16, which means high band 6, closest state rank. So you've either been exposed to it and able to do it. You've never been exposed to it, you won't be able to do it. Same thing with these partial fractions. I can show you what they will give you as part A, which is fine, you'll be doing it. But in case it's not a part A, and in case they just want to put it towards the end as a hard question, extension 2 students will find it easy, but extension 1 students will struggle. So let's learn it. That's what I'm trying to say. All right. So this is fine. Integral of 1 dt is t plus c. This bit here, we're going to focus on now. Only this bit here. So this bit here, think of it like this. 1 over rp minus p. That can be written as a on rp plus b on 1 minus p. So pretty much we're going to split this into 2 different fractions, which before we could never do. But now we're going to be able to do it, as long as a and b are constants. And those are the constants we want to find. What are those constants? Well, at this stage, we want to write equating, for example, numerators. All right. What's your numerator on your left-hand side? 1. What's your numerator on your right-hand side? It's not a plus b. Your numerator is a multiplied by 1 minus p, because you would have to make this into a common denominator, right? So again, in orange, technically, this is a 1 minus p plus b rp on rp 1 minus p. So my numerator is 1 equals a 1 minus p plus b rp. Okay? Obviously, Anouk, what would you let p equal to first now? Let p equals to 1. Why do we do that? When p equals to 1, this bit disappears. You'll be able to find b. So let's do that. When p equals to 1, you get 1 equals, this bit disappears, you get br. And therefore b equals 1 over r. Andy, do you want to take a guess at the next one? Let p equal to what? To get rid of this one. 0. Do you get the logic? You're literally trying to get rid of the other letter. So 1, you get rid of a, you'll find b. Then you'll get rid of b, you'll find a. So let p equal to 0. You write 1 equals 1 take away 0, which is just literally a. So a equals to 1. So now this bit in orange, which I'm going to change it to green, this bit can now be written as a over rp plus b over 1 minus p. where r is just a constant and p is your actual variable. So something that we couldn't integrate before can now be written in terms of two fractions, which hopefully we can integrate. Okay, again, as a 3-unit, let's say band 3, band 4 question, yeah, they will say given, part A, prove this is equal to this. And all you would have had to do is cross multiply and then just said that this becomes that. That would have been easy. So green becomes orange. But as a harder band 6 question, they're going to say what we just gave you up here, which was write n as a function. So you are going to get stuck when you're about to integrate. If you don't know partial fractions, which now you have semi-learned. You don't need to know the other two types for this course, just this type. Okay, back to it. So back to where we were at, which was this line in black. The integral of dp, wait, any questions from what we've written so far? The integral of dp rp 1 minus p, which equals to t plus c so far. That's where we're at. That's our last line. All right, this line on the left-hand side can be written as, that in green, 1 over rp plus 1 over r1 minus p dp. And then back to equals t plus c. Yes? Hit me. 1 over rp. How do we integrate that? What does that become? Remember, r is just a constant. So think of 1 over p. ln. So the answer is 1 over r log p plus, what about the next one again? 1 minus p in brackets. Also ln. So, but because you got to differentiate the inside, it's negative. So it's negative 1 over r log 1 minus p equals. Oh, by the way, you know that log curves, logs and exponentials, are they're 100% going to become logs. That's a given. But anyways, ln's. Is that okay? We're trying to solve for p. We are trying to solve for p. Before I can do that, I need to get rid of the constant c. So initially, when time is 0, population equals well, it depends on the case. Doesn't really matter. When t equals 0, population equals p naught, any constant. I don't know, but let's not confuse ourselves. Let's use a. We don't know. It's just it equals to an initial value of population. All right. No, I'm about to overkill that. No, don't like it. No, then leave it. Leave it. Sorry?
There's people in.
Yeah, leave it. It's fine. Just leave it. Leave it like that. Leave it. Let's not overkill it. Leave it. Sounds good? Because we're gonna replace that for our capital A at the end. That would have made it a lot more complicated, because then you would have had this much of a constant. You would have all these logs, where at the end we're just going to replace that for capital A anyways. So to avoid that, just leave it. That's it. Don't worry. Back to it. It's fine. Go back to what we want to find, which is P. If I want to find P, what's your next step? What are you going to say?
The logs are minus t.
That is exactly what I'm going to do, and multiply by the r, or straight away. So log, make it into a fraction. So P over 1 minus P equals RT plus RC. There's not a question. No. I'm showing you for a generic case, like this one here. This is for a generic case, how to go from here to here. And if you're able to do that for a generic question, then you'll definitely be able to do it for an applied question like this. And you'll be able to do it for now, hopefully for this one here. Because I realized we didn't actually do integration last week. We only did the derivatives last week. So we're here. We're very close. Obviously, what are you going to do now? We're solving for P. Exponential. ERT plus RC. So good. We're solving for P, as I keep saying. What are you going to do now? I'm going to multiply the denominator over. You probably be like, well, that doesn't do much, but watch. P equals ERT. I'll do it slower. On 1 minus P. Okay. Can we see that that's plus RC? What am I going to change that to? Multiplied by ERC, and then ERC becomes capital A. Right? Remember, because what we said last week was we can write any exponential, any constant as capital A. You got to get that in your head. So instead of me, you know how before I was going to write initially, like I said, my constant would have been this big. Ready? That's how big my constant would have been. Why would I have done that when right at the end here, I'm just going to replace the whole constant for A. It just would have been silly. So we usually leave it. ERC becomes A. So I'm at this stage. P on 1 minus P equals ERT multiplied by A. Now we multiply it over. P equals AERT 1 minus P. Expand. AERT minus APERT. We don't want P on the right-hand side. So what do I do now? Say it again. Take it over to the left-hand side. So you get P plus APERT equals AERT. What do I do now? Factorize the P. We're very close. AERT equals AERT. P equals AERT on 1 plus AERT. Very, very close. We can't have the T on the top and the T on the bottom. So look at it. Wait. Where is it? There it is. They look like that. They look like more like 1 AE negative RT. What the hell? Negative. Okay. Scratch your head for a second and then think, I've got this. You're one step away. I'm just going to say, do this, and you're going to get from here to the answer. Who's going to be creative? Like that. Creative. Or you just keep telling yourself, how do I get from this to this? What would I have done to move from that to that? From a numerator of that to a numerator of this. Wait. Which one do you mean times? From the top line to get to the bottom line? And if you're saying yes, then how? Times in it by what? I'll re-say the question. How would you change AERT to the number 1? That second one. Factorize, yes, if there was common factors, but there aren't common factors on the top and the bottom. You're going to say divide. What happens when you divide the top by AERT? What happens when you divide this guy by AERT? Just this guy, just this one. Just this one. That one becomes 1. This one becomes negative RT. It becomes 1 on A, technically, but then 1 on A can also be written still as A. You get the logic on that? Because 1 on A can be is a constant, which is just A anyways. Yeah? Are you sure? Because to you that sounds very counterintuitive. You're like, but then my whole life we've been saying like X is not the same as 1 over X. But how come all of a sudden I'm allowed to say X is 1 over X? But X is technically not 1 over X, but if we're going to group them both as and say, are they both variables? Well, if X is a variable, is 1 over X still a variable? Answer that question. If X is a variable, is 1 over X still a variable? Yeah. So then can X and 1 on X be the same? Well, as long as they're both variables, they can potentially be the same. If X is 1, it can definitely be the same. You see that logic? So you're done. All you have to show is that division ART equals to this. All right. So this was actually quite, I guess, challenging.